Van der Waals equation for calculating the pressure of a non-ideal gas is P plus a n square divided by V square into V minus Nb is equal to nRT. Van der Waals suggested that the pressure exerted by an ideal gas, P ideal, is related to the experimentally measured pressure, P real, by the equation P ideal is equal to P real plus a n square divided by V square. That is basically, this was the correction term, okay, in the observed pressure. The constant A is a measure of intermolecular interaction between the gaseous molecules that gives rise to non-ideal behavior and depends on how frequently any two molecules approach each other closely. Another correction concerns the volume occupied by the gas molecules. In the ideal gas equation, V represents the volume of the container. However, each molecule does occupy a finite, although small, intrinsic volume. So, the effective volume of the gas becomes V minus Nb, where N is the number of moles of the gas and B is a constant. The term Nb represents the volume occupied by N moles of the gas. Having taken into account the corrections for pressure and volume, we can rewrite the ideal gas equation in the form of the Van der Waals equation, having the corrected pressure and the corrected volume. Okay, so let's move on to the questions. At relatively high pressures, the Van der Waals equation of state reduces to. So let's first rewrite our Van der Waals equation according to the passage. It was P plus a n square divided by V square into V minus Nb is equal to nRT, right? Now, when the pressures are very high, generally the order of this A is around 0.5. So when the pressure is very high, this term gets neglected, right? Due to that, the equation reduces to P into V minus Nb is equal to nRT. And if we convert the volume into molar volume terms, so it will be P into V molar minus B is equal to RT. That is dividing by N on both the sides. And simplifying this equation, we can write PV minus PB is equal to RT. Okay, and PV is equal to RT plus PB. That is option D. For non-zero value of force of attraction between the gas molecules for large volume, the gas equation will be. So let's rewrite the equation. P plus a n square divided by V square into V minus Nb is equal to nRT, right? And when the force of attraction is not negligible, right? It is non-zero. It means that the a n square divided by V square term would contribute. However, it is for a large volume, which would mean that this Nb term is approximately 0. That is, we are not accounting for the volume of the individual particles. So the equation would become Pv plus a n square divided by V is equal to nRT. That is, Pv is equal to nRT minus a n square divided by V. And if we look at the options, this is exactly same as option A. So that becomes our answer. The Van der Waals constant A for carbon dioxide gas is greater than that of hydrogen gas. It means that. Now we have been given that A for carbon dioxide is greater than A for hydrogen. Now if we try to remember what our passage said, it said that A is a measure of the intermolecular interaction, right? So higher the A, higher would be the intermolecular attraction, which means that the attraction between molecules of CO2 is greater than the attraction between molecules of hydrogen. And higher attraction would mean easy liquefaction. Okay, which means that the carbon dioxide can be more easily liquefied. So the answer will be option C. Using van der Waals equation, find the constant A when 2 moles of a gas confined in 4-liter flask exert a pressure of 11 atm at a temperature of 300 Kelvin. The value of B is 0.05 liter mole inverse and R is given to be 0.082 atm liter per Kelvin mole. So let's write the van der Waals equation. It is P plus AN square divided by V square into V minus NB, and this is equal to nRT. And just plug in all the values which are known to us. P is known and is given to be 11 atm plus A is unknown. N, the number of moles, is given to be 2. So 2 square will be 4 divided by the volume is given to be 4 since it's a 4-liter flask, multiplied by the volume again is given to be 4 minus the number of moles is 2 into B is given to be 0.05 is equal to N, that is the number of moles, 4 into 0.082 into the temperature is given to be 300 Kelvin, right? So let's just cancel things out. 11 plus A multiplied by 4 minus 2 times 0.05 will be 0.1 is equal to 4 times 300, that will be 1200 multiplied by 0.082. So we can write it as 11 plus A is equal to 1200 into 0.082 divided by 3.9. Okay, and A will be this entire quantity into 0.082 divided by 3.9 minus 11. And when you solve this, you would get the value of A to be 6.46. And so our answer would become option D.